Welcome back to linear algebra. Let's go. What do we got? If the matrix B results from the matrix A by performing one elementary row operation, how might you recover A from B by performing one more elementary row operation? Okay, if you swap the rows again. If you multiply a constant through a row, multiply a reciprocal of that constant through that same row. If you added a constant times a row to another row, subtract that constant, or multiply the same row by the constant, subtract it from the row instead of adding it. All right. State 3 results that are equivalent to the statement that A is invertible. A can be represented as a product of elementary matrices. The row echelon form of A is I, and AX equals 0 has only the trivial solution. If the elementary matrix E results by performing a certain row operation on the identity matrix I, how is the product EA related to the matrix A, assuming that the product is defined? It's like whatever elementary row operation you would use to get E from I is the same elementary row operation. Essentially, if you use that same operation on A, that's what you're going to get. What is a row matrix? A row matrix is a matrix with only one row. Yeah. An elementary matrix is a matrix that can be the square matrix that you can get from an identity matrix using one elementary row operation. Essentially, it's a matrix you can get from I with only one, or exactly one elementary row operation. What does it mean to say that the matrices A and B are row equivalent? Is to say that A and B are row equivalent is to say that you can get one from the other, or the other from, you can go from back and forth. You get one from the other, vice versa, only using elementary row operations. If E is an n by n matrix, how might you obtain the inverse of E from I? Oh. You basically do the opposite. Whatever elementary row operation you do to get E back to I, to undo E to get back to I, you're going to apply that operation to I, which is the whole thing we already talked about, swapping or multiplying by the reciprocal or subtracting. All right, that's it for Anki. I think I'm going to grade what I did yesterday, then I'll be back to continue doing more practice problems after that. All right, I got that problem from yesterday correct, so I'm going to continue doing more practice problems. I'll be back in a bit. All right. Review problem from 1.4 was basically verifying that this is true. A product of a scalar in a matrix, transpose of a product of a scalar in a matrix is equal to the same scalar times the transpose of the matrix, which we verified to be true with the examples given. This was finding an A value where a matrix that satisfies the equation A to the -2 equals 9, 4, 1, which we found to be this is a possible one. I think, yeah, we probably could have done -1/3, -1/2, -1/2 as well, because they get canceled out. This one was like, if A is equal to the matrix where A equals sub ij, and A sub ij equals I squared plus j squared, is it symmetric? Well, I just did a little bit of writing, testing, and then thinking, and yes, it is symmetric. And now we're on a proof, which the proofs are the most difficult part for me because I've never done any proof writing outside of this book, but we're going to try anyway. Every square matrix A can be expressed as the sum of a symmetric matrix and a skew-symmetric matrix. So I don't know how to do this, but they give you this identity. This is definitely part of it. Okay. Hold up. I might have figured something out here. All right. All right, I think there's gonna be something to do with like canceling things out here. Yeah, it's gonna be something to do with plugging in things for the transpose of B being equal to B, vice versa for a symmetric matrix, and this is and then the transpose of C being the negative C, and also A. Actually, A, not so much for A because A is not necessarily symmetric or skew symmetric, but anyway, I'm gonna keep working through this tomorrow. So talk to you then. See ya.